We start our adventure with a view of the projection of all galaxies within 8,000 km per second in the V8K redshift catalog. The projection is in supergalactic coordinates, with the plane of the Milky Way slanting at a steep angle across the center and wrapping around the edges. The nearest galaxies are in dark blue and concentrate around the Virgo cluster on the supergalactic equator to the right of center, or around the Fornax cluster in the lower left quadrant. One of the two most prominent filaments is the Pavo-Hindus structure in cyan and yellow that can be followed from near the Virgo cluster across the zone of obscuration, rising increasingly above the equator toward the left. The other most prominent structure is the Perseus species filament in yellow and red, rising at a sharp angle to the extreme left. Where do these galaxies lie in 3 dimensions? That's seen as we transfer galaxies from the 2-dimensional projection to a 3-dimensional cube. The galaxies end up at their positions in redshift space. Kinematic stretching in clusters has been truncated. Positions of galaxies within 3,000 km per second have been modified in accordance with a model of galaxy streaming around the Virgo cluster. The Perseus species filament is the prominent structure in the foreground of this view. The complexity of what we are seeing is overwhelming. Let's get grounded by a visit to where we live. We are now approaching the Milky Way, represented by the blue dot. The scene is now centered on the Milky Way, with its entourage of small galaxies and adjacent Andromeda galaxy with its own entourage. Other nearby groups are identified. There are good distance measures for most of the galaxies in this scene. These nearby galaxies are positioned in physical space with positions in velocity coordinates of distance times Hubble constant. We are looking at a cube that extends to 6 megaparsecs. The rotation of this scene allows us to see that most of the galaxies in this local cube lie in a thin plane, the equatorial plane in the supergalactic coordinate system. There is a very empty sector above this plane, the local void. We call the flattened distribution of nearby galaxies the local sheet, and we see that it is a wall bounding the local void. Returning to a polar view of the local sheet, the scene expands to include the Virgo cluster. The local sheet trails off in density beyond our location in the direction away from the Virgo cluster. Our inventory of accurate distances is severely diminished beyond 500 km per second. With the next scene, we draw back to see a polar view of the entire width and length of the V8K catalog, though what is shown is only a line-of-sight slab 2000 km per second thick, centered on the supergalactic equator. The most prominent feature is the crowding of galaxies in a horizontal band just above center, running left to right, from Hydra Centaurus through the Virgo cluster to the Ursa Major cluster and beyond. Other prominent features include the Fornax cluster region, Perseus species, and the southern wall Pavo-Hindus and a slice through the Great Wall. We rotate 90 degrees and re-slice to a slab 1000 km per second thick. The slice includes the Virgo and Fornax clusters, the local sheet, and local void near the center. We see intersections of the Great Wall on the right and the Southern Wall at the left. There are strikingly empty regions like the Hercules void and the Sculptor void. Another 90-degree rotation and a 2000 km per second thick wrist slice gives us an edge-on view of major components of the Centaurus Hydra Virgo supercluster complex. The linear structure seen in the polar view that ran from Centaurus cluster through Virgo to Ursa Major now is seen to consist of several separate strands, layered in supergalactic Z. The main features are the horizontal filament on the supergalactic equator and the pronounced Antlia wall that runs down from Centaurus cluster to Antlia cluster and then turns horizontal in this view. Again, voids are seen. The microscopium void is especially evident. The scenes that have been shown give an inflated impression of the importance of the local region. We are aware of objects nearby that are unnoticed far away. It can be anticipated that the distribution of galaxies, large and small, is roughly the same at all distances in the small patch of the universe that we are considering. Here we compensate for the increasing loss of galaxies as a function of distance. We don't know exactly where the missing galaxies lie, so we associate them with the galaxies that are seen and then smooth and show contours of the smooth density field. Now the local region appears dramatically reduced in importance. The main structures are the Great Wall and the Perseus species filament with the Southern Wall. Pavo Indus is significant too. A rotation takes us close to a polar view. We see the importance of the Great Wall and the Hercules cluster region within it. The Perseus species filament is important and we see its connection with the Southern Wall. The local supercluster is not so important. The next series of images gives focus to the central region of the supercluster complex that we live in. The Centaurus cluster seems to have a special place, where 5 strands are converging. In this polar view, galaxies in major clusters are color red. Otherwise, galaxies in the 5 strands are given distinct colors: green, pink, purple, orange, and blue. The blue strand bifurcates into 2 branches as it crosses the zone of avoidance. The convergence of the 5 filaments onto the Centaurus cluster is seen best with movement of the viewing angle. The scene reminds us of the many arms of an octopus. There is a vertical wall of galaxies in this view that includes the Centaurus, Antlia, and Virgo clusters. See how the local void is bounded by two of the strands from Centaurus. The presentation now transitions to representations of the velocity field. Only a fraction of the galaxies in the redshift catalog have accurately measured distances. In the present analysis, our distance measurements are limited to the volume within 3000 km per second. We begin with a polar view of a 3000 km per second slab in thickness. An arrow is attached to each galaxy with a measured distance. The new reference frame is Hubble expansion with respect to the cosmic microwave background. Deviant or peculiar motions towards us are shown as blue arrows and deviant motions away are shown in red. We see an obvious dichotomy. Galaxies to the right of the Milky Way tend to have blue arrows, while galaxies to the left tend to have red arrows. There is evidence of a flow that picks up speed from right to left. The scene now evolves to a representation of the deviant motions derived from a Wiener filter model of the velocity field. The vectors of motion are now three-dimensional, constrained by observed line-of-sight motions where they exist. The Wiener filter model provides an expectation peculiar velocity for every galaxy in the redshift sample. Another transition replaces the individual vectors tagged to galaxies with velocity flow lines and adds color to the background to represent the Wiener filter density field associated with the velocity pattern. High density regions are represented in red and voids are blue. We remark on the importance of the region around the Centaurus cluster. Now there is a 90-degree rotation and the slab being considered is 2000 km per second thick, capturing the wall of structure running from Centaurus and Antlia through Virgo and Ursae Major. Again, the map of observed peculiar velocity reveals the right-left dichotomy. Blue arrows towards us on the right, red arrows away on the left. We transition to the representation permitted by the Wiener filter model, with three-dimensional peculiar velocity tags given to all the galaxies in the redshift catalog. And then transition to the representation of flow lines and the underlying density field. Again, we see the importance of the region around the Centaurus cluster. Densities go to green, the mean density, beyond the domain of the measured density constraints. For completion, we view in from the third orthogonal direction, looking at a slab at the midplane of the data cube. The dominant motion is away from us now, so the red-blue vectors are more scrambled. The processing by the Wiener filter reveals the pattern of flows. The Centaurus region is to the background of the slab that we are viewing. Now we see the streamlines of motion and underlying density field. Particularly note the outflow from voids and the particular prominence of the local void. The present analysis must fail to represent the true extent of the local void, because it extends beyond the domain of distance measurements. The Wiener filter reconstruction returns to mean density where there are no constraints. We end with a fanciful view of the supergalactic equator.